Hey guys, welcome. So thanks for joining me. I am doing some walkthroughs for you guys for the labs. Since we're not actually doing the labs together in person, I thought it would be a good idea for me to do walkthroughs like I do for my online students. So that's exactly what I'm doing here. The way that this will work is that I will do a little bit of an introduction for the labs. I'll talk a little bit about how it connects to the materials that we've been talking about in the lecture. We'll do some here's what this is why we're doing this, walk through the beginning of, hey, why, the, this is, the introduction to the lab. Not that you can't read it, but I'll say, here's the intro, here's anything that I think is really important out of that. I'll try not to read the whole thing. And then I will actually do the lab and you can watch that. Now, it's going to be really boring. I promise you, it's really boring. But my purpose in doing this is so that you can see what trips me up. So if you're doing the lab and you run into an issue, you can see that I'm doing this and you can fast forward to whatever part you're having problems with and say, okay, wait, this is where Nan's doing this part. Let me see what she's having problems with. You can see how many sig figs I put in for each answer. So you can go, okay. And I'll usually talk about why I put in the number of sig figs that I put in there. Or, it like maybe it'll trip me up and I'll put in something and I'll go, wait, it didn't want that. And I'll talk about why I changed it. Excuse me, or complain about what it's doing because I do that a lot. And I'll talk about, why it's doing what it's doing or whatever. Um, I'll talk about how you can get information about how to do the calculations that you need, where that information is, and how I think you should keep what I call a lab notebook so that you'll have the information that you need to do the post labs. I'll talk a lot about that because I do think it's important that you keep this information together so that then you can refer to that to do those post labs. Because if you don't keep that information, you're not going to pass the post labs. That's it. You won't. So it's important that you keep that information. So I'll try and show you how I do that and give you some options for how you could do it. So it's up to you how you take care of that, but that's what I'm going to show you. So I'm going to go ahead and share my screen so that you can see what I'm talking about. Get this out of the way. And what I'm looking at here, this is a preview of the experiment. So this is equilibrium 1. I'm going to go ahead and do a start on this one. And actually, I'm going to come out of this. Hey, where'd it go? I'm going to come back in here. And what I'm going to do is I'm instead going to go to student view. And then I'm actually going to perform it this way because that way I can see that I've actually done these things. It's a stupid thing, but for me, it's an OCD thing. So I can see that I have chemical equilibrium that I need to do, and I can go in here and actually perform this experiment rather than doing it from the preview. Oh, that's not what I want because that's not work. So let's back out of this assignments. Scroll down, post labs, virtual lab. This is the tutorial, and that one I already have a video posted for. This is the virtual lab one, which is in progress. So come in here. I opened this last night because I was going to record this last night, ran into some issues and didn't actually finish it. So in the introduction for this, we talk a lot about what is equilibrium, how do you set up an equilibrium constant, and then we talk about the Beer-Lambert. Now, we haven't talked about the Beer-Lambert, so I want to take a minute to talk about this. The Beer-Lambert law talks about the relationship between the absorption of light and the concentration. So just from a pure, what you experience in life standpoint, you know that the higher the concentration is, the less light is going to get through it. So the more material you have in that solution, the less the light will go through because it's more opaque. And so you'll have less light that gets through it. So the higher the absorption will be, for the concentration being higher. And so that's what the Beer-Lambert law states. Now it's got a couple of components that are in it, one of which is this epsilon, which is this E right here. And that's called the molar absorptivity. And that's a relationship that is based on the nature of the solution. So those are tabulated values that we can go and find, or we can calculate them. Okay, so those are things that we can look at. And the other thing is this L, which is the path length in centimeters. It's usually set up so that the path length is 1, because then we don't have to worry about it. The concentration is always given in molarity, because then the molar absorptivity is in molarity also, so 1 over molarity, and that way we can get rid of it. So that makes our lives easier, okay? And it's always done at the wavelength of highest absorption. So that way we get the maximum signal out of this particular thing that we're trying to measure. So we want to maximize the signal that we're getting. And so we do it at the place where we have the highest response for the solution that we're looking at, okay? So when we talk about taking data from instruments, we have to figure out, what's the best way for us to do this. And one of the considerations that we have to make is if we're trying to measure on a colored compound, we know that there's a spectrum of wavelengths of light that we could be using to look at that. And we have to pick the one wavelength that's going to be the best choice for us. And we choose the one that has the highest absorption for that particular material. So, and we use that same wavelength to do all of our measurements. Now, in addition to looking at that Beer-Lambert law, which has, and I'm going to show you this lovely graph over here, the Beer-Lambert law generates a linear relationship, so that if we take and make a concentration and we plot that versus the absorption, okay, so concentration is down here, absorption is here. So I make a concentration versus absorption plot. It should be linear. Now it's not linear everywhere, okay? So it's only linear in certain portions. Down at the very low concentrations, it's not going to be linear. It's going to have some deviations down there. And at the very high portions, it's not going to be linear. It's going to have big deviations up there. So there's a range over which it's linear. And we can use that. If we're outside of that range, it's going to be problematic. And if we're trying to solve for something outside of that linear range, that's going to be problematic too. So there is a limitation to how we can use this data, okay? So if we're asked to, interpolate past the data that we have, then that's going to be a problem, right? So we can only use the regions where it's defined. So we have to get the best calibration curve that we can. And of course, we can try this beyond this data and see where it goes, but then it becomes problematic to see if it's actually linear or if it just creates a bad line. And if we don't take enough data points, then it's hard for us to tell if it's linear, really linear, or if it's just deviating from linearity and we don't know because we haven't taken enough points. Okay. So that becomes problematic too. Okay. So we take as many points as we can and we create a calibration curve. And that's the first thing we're going to do in this lab is create a calibration curve. Once we've created that calibration curve, then we can use that calibration curve to look at what is the actual concentration of the colored species that we've made to measure that concentration for that colored species. So we force the equilibrium for the formation of this particular compound all the way to product by making one concentration really, 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 really high and the other one fairly low. And so that way we know exactly how much product we've made because it's based on our limiting reactant. Oh, that limiting reactant, yes. So that determines exactly how much product we've made. And so we know exactly how much product we've made for that. And so we can base our calibration curve on that particular limiting reagent, and that determines how much we've actually been able to make. Then we can turn around and mix things together so that we can see, okay, where does this give us points on this equilibrium curve? Okay. And we can study the equilibrium by looking at what is the concentration of the product. So if we're looking at Fe3 plus SCN minus, making FeSCN2 plus, then this colored species, the FeSCN2 plus, that's our colored species. The formation of that, whatever that concentration is, we can measure directly. And of course, if we know what the initial concentration of the Fe3 plus is, and we know what the initial concentration of the SCN minus is, then we'll be able to figure out what their equilibrium concentrations are using the ice tables, just like we talked about in class. So we'll be able to find what our K is for each run. And so we can do this for multiple points. And so we can determine what the K is for each of those points, and then see what the average is of each of those points. And once we've determined what those values are based on our calibration. Now, the only thing that's weird about this is normally when we use our spectrophotometers, what we do is that we take and we make just the measurement of this lovely colored solution with water as our background. So we have to account for any absorption of light from the water. Okay. The problem with this is that the Fe solution has some color of its own. So the Fe solution is yellow. Water is clear, the KSCN is clear, but the FeNO3 is yellow. And so we have to use that FeNO3 as our background, because if there's any of that left over, then we have to subtract that out. We have to correct for that. So it's kind of like tear. When we use our balances, we have to get rid of that part, right? So what we're going to do is put that in as our blank. And so we're going to calibrate the machine with that as our background. So that way, if there's any in there, then the solution, whatever we measure for this, the solution that we've made will be subtracted from it. And if there's not any in there, then it doesn't matter. So that's how we're going to correct for that. Right? So that's something else to keep in mind. All right. So that should take us through everything. Now, if you want to look up more information about the Beer-Lambert law, it is available pretty much anywhere in the universe. It's out there on the interwebs. It is available in your textbook. There is a thing in the appendix of the lab manual that talks about the Beer-Lambert law, so you can look there. It's a very useful tool. We use it a lot in spectroscopy to talk about the absorption or percent transmittance, either one, and their inverse. The absorption and the percent transmittance are inversely related to each other, so we can measure one of them. So that's useful. Okay. So this is our setup. And of course, we've got a whole bunch of stuff here. So I can use the show labels to show me exactly what all of these things are. Now, I use that a lot because I'm kind of blind and I can't always see things. So I use those from time to time. The instructions tell me exactly what to do. So 10 milliliter graduated pipette to transfer 10 mils of the 0.40000 molar iron-3 nitrate to the stock beakers. I take one of these, I put it into this solution right here, I select the 10, I then pick this up and I put it into the stock, and then I put that into the waste, okay? And I record that in my lab data. So I'm going to pull this lab data down so that I can look at this. Concentration of that was given to me, and that's 0.41234. And that's in molarity. It's already listed there. The color of that solution is yellow. And that's why I pulled it down, because I wanted to make sure I could look at it. I don't like to remember. I like to make sure that I'm actually looking at it, because I want to record exactly what I see. That's important to me. I was trained to do that, so that's why I'm doing it the way that I'm doing. It's a good habit for you to get into. Concentration of potassium thiocyanate, that's this guy right here. Potassium thiocyanate is that guy. What it says about the potassium thiocyanate is that it's 0.00300 molar. Okay. Now remember, we're making this solution, we're driving this reaction all the way forward by making sure that one of these concentrations is huge, this one is huge, and the other one is fairly low, this one is low. So our thiocyanate is what determines how much product I can make. Okay. Color of the potassium thiocyanate is clear. We'll call it colorless. The volume of the iron 3 nitrate is 10 milliliters. And it gave me 4 sig figs, so I'm going to put the 4 sig figs. The volume of the potassium thiocyanate, which I haven't done yet, it says 2.00. So now I'm going to take this one, I'm putting that in the potassium thiocyanate. It says it wants 2 milliliters of that. I'm going to pick this up, I'm going to put it in here, and I'm going to move that over there. Now notice it's turned bright red because of that reaction, giving me that FeSCN2 plus, which is red. I'm not quite done yet. It says use the 10 milliliter cylinder and pipette 8 milliliters of DI water. So here we're going to go 8. I'm going to pick this up and put this over here. We diluted that a bit. And now we're going to take the stir rod and mix that together and put that in the waste. And then we want to calculate the concentration. Now I need to put in that I put 8 milliliters of that, and I want to calculate the concentration. Okay. Before we go any further, I want to show you a couple tools that you have available to you. So what I'm going to do is I'm going to scroll all the way down to the bottom of this data thing. So there's a bunch of data that you're going to collect. But down at the bottom of this, you're going to see there's a whole bunch of little pieces of info down here. And it says how to calculate this, iron 3 cyanate, how to calculate it, how to determine, yada. If I click this, it gives me this piece of information. Now, I'm going to go ahead and do this snippet, this thing, so that I can take a snippet sketch. I want to get that, and I want to copy that. And then I'm going to take it and I'm going to put it over here. So what this is OneNote. And I use OneNote to make myself a virtual lab note. And so I say, okay, this is the first bit that they give me to explain to me how to do the calculation that they've just asked me to do. And I put this in here because I'm probably going to get asked to do this on the post lab. So I learned how to do this in the process of doing this lab. This is how I do it. So I may have to do this again on the post lab. So it is perfectly okay for me to refer to my notebook that I have now put together to know how to do this. This is my notebook that I am putting together. I don't care how you do it, but that's how we do this. Okay? If you were in a 111 lab, in a physical one, we would be asking you to keep a physical lab notebook. And you would be expected to write all this stuff down. Okay? So not only would you have your data tables, but you would be expected to keep a lab notebook. And then you could use that lab notebook when you're taking the post labs. So on this, that's what I'm doing here, is I want you to use this information to pass those quizzes. Okay. So now I can move this down. I can actually keep this up if I need to. But what it shows you is that this is going to be one of these times where we're going to use that concentration times the volume. So the way that I talk about this, and the way that you'll see this in the exam handout, is a dilution thing. Let's please connect. I want you to connect. And so in the exam handouts, the formula you'll see is M1 V1 equals M2 V2. Now the way that they have written this is C2V2 equals C1V1. Okay, so concentration times volume equals concentration times volume. It's just a slightly different way of writing the exact same thing. Okay, okay, fine. What this means is that the molarity of your first solution times the volume of your first solution is equal to the molarity of your second solution times the volume of your second solution. I want to know what the new molarity is. So I'm actually going to solve for M2. It's going to be equal to the first molarity, is the first volume, divided by the second volume. So let's take a look at that data that we collected. So the data that we collected, look at our data over here. The concentration of that, the iron thiocyanate that we had, the concentration of that was that 0.4000, right? But let's look at the information that they gave us and see what they're talking about. So are we talking about that 0.4? Stock solution mixes a small amount of KSCN with large excess of FeNO3, which drives the equilibrium reaction far forward to the products. Assume that essentially all of the SCN minus present forms the FeSCN product. So what they're saying is that the concentration of potassium thiocyanate is what determines how much product you make. So we actually need to be looking at the information about the thiocyanate to do this. So I need to be looking at that thiocyanate data. So my thiocyanate data, that concentration, molarity of that is that 0.00300 molar. And the volume of that I used was 2.00 molar. Now the total volume, when I'm done, all of those volumes added together, V2 is equal to 10.00 milliliters plus 2.00 milliliters plus 8.00 milliliters, which is 20.00. So now I can take my M2 is equal to the M1, 0.00300. My V1 is 2.00, and my V2 is the 20.00. So that's the calculation. Oh, sorry, you can't see that. That's the calculation that I need to set up. So the molarity was the 0.00300 molar. The volume of that solution was the 2 milliliters. Total volume is the 10 milliliters of the FeNO3 plus the 2 milliliters of the KSCN plus the 8 milliliters of the DI water. That's 20 total. So I take my M2 is that 0.00300 molar times the 2 milliliters of the KSCN divided by the total volume, which is 20 milliliters. That's the calculation that I need to do. So I'll pull up the silly calculator that I've got here. 0.003. I can put in those zeros times 2.0 divided by 20. And that gives me this lovely number right here. Equals 0.0003. Now, I look at that and I say, okay, how many sig figs should I have on this number that I'm looking at here? Well, let's think about this for a second. How many sig figs are in this number? that particular number right there has 4 sig figs. Okay. This particular number here has 3 sig figs. So the 2.0 has 3. This has 4. This right here has 1, 2, 3. So my answer should have 3 sig figs. So this is the only sig fig I have in my answer. So I need to have 2 additional zeros on it. So this is the answer that they are looking for. So I need to, because the zeros in the front are not significant. I could get rid of them by putting this into scientific notation. 3.00 is 10 fourth. I'm going to do that because the ALEKS in the lab format will not allow that. Okay. So here I cannot do that. And so when I put this concentration in, it has to be 0.000300. And the color of that stock solution, because that's the only thing that's even close to red. And when I click out of that, I see that nothing is red. So since nothing is red, that indicates to me that I'm probably fine. If anything was wrong, it would be highlighted in red. And I can show you that because if I click this and I had said clear, it looks like this. It says clear describes when a substance is transparent or unclouded and is not used to describe lack of color. So colorless. So there you go. Now, so now you can see that's what it's going to look like when it doesn't like what you've done. If we had come in here and put this as 0.003 and come over here, it doesn't like the number of sig figs that you get. So if you come over here and it doesn't freak out about anything, then it's fine with your sig figs. Okay? Fine with your sig figs, fine with every description that you've done. There you go. Okay? So now we can look at that. We've gone through this phase, so we can go, yay, I'm done with this. So use the 5 milliliter graduated pipette to transfer 4 milliliters of stock solution to each test tube. Do that again. I've recorded my volumes. Now I'm going to transfer some DI water. Hopefully it'll let me record this. I can minimize that. So I'm going to take this, I'm going to put it in the DI water. I'm going to do 1 in test tube 1. So that goes in here. Now I'm going to take up 2 and put that, yes, I'm here, and put that in test tube 2. And then I'm going to do 3 in test tube 3. Now put this back. You get a clean stir rod. Mix this one and get rid of the stir rod. So we don't want to cross-contaminate. We need to make sure that we use a different one for each. Now we want to calculate the iron thiocyanate for each solution. So I'm going to go to my lab data and say, okay, I don't know what to do now, but how to calculate initial concentration of iron, 3 ion, and thiocyanate. So, okay. So now I've got some data. And I'm going to take a picture because I might need this. I don't know. I'm going to put this over here. But in looking at this, I haven't added the SCN, I've just added water. So I don't think this is going to apply yet. But this, we're just added water to it. So I've got a concentration initially, and I've added, we've got a different volume. This probably still applies. So let's use that. So I'm going to close that. Say, okay. So I use the volumized SOC solution. I'm going to pull up is this. So I have 4 milliliters of that stock solution that I've used for all of them, right? And the molarity of that solution we calculated to be 0.0000300 molar. We calculated that right there. Okay, so we know that that's it. And the total volume for each of these test tubes is going to be a little bit different. So for this one, it's going to be 5. For this one, it's going to be 6. And for this one, it's going to be 7. So my total volume here is going to be 5 milliliters. And so if that's true, and I'm solving for M2 again, I've still got that M1 times V1 over V2. And so it's going to be that 0.000300 molar times that V1, which is 4.00 milliliters, over that V2, which in this case is 5.00. So that's what it'll look like for that first container. So take that number that I calculated and multiply that by 4, and then I can divide that by 5. And that gives me M2 equals 0.00024. Now, how many sig figs should I have? Again, at this point, 3, because there are 3 sig figs in this number right here. 3 right there and 3 right there. So I'm still looking at 3. 1, 2, and now 3. So that's the number that I should be reporting right here. 0.000240. Now the next calculation should be almost exactly the same. The only thing that's going to change 0.000300 molar times 4.00 milliliters, because that's still the initial volume that I used of that solution. But my new total is now 6 milliliters. And so we're going to have, so this the second solution is going to be 6 on the bottom. Then one after that will be 7 on the bottom. And so I'm going to set up those two calculations. Zero point 0.0003, which is the number that I calculated there. Four divided 6, which gives me this 0.0002. And I need to add 2 more zeros at the end to get 3 sig figs. So I'm going to record right here 0.000200. That's one of them. So now I'm going to take 0.003, multiply that again by 4. And now I'm going to divide it by 7, which is that total volume. 4 plus 3, 7. Which gives you 1.714 times 7 minus 4. So if I'm looking at that, that's 6. We want that to be 7. Thank you. Seven. 1. That's what I believe that should be going to be. Let's see if I'm right. 0.1234171. Let's try that. No, too many zeros in the front. Sig figs. Move the decimal too far. I'm not good with sig figs, or with scientific, moving between scientific notation. Not good with that, so apologize. So those are those numbers that we have for that. And when we look at our calibration curve, we've made these solutions, and now we want to compare those. What we're going to do is put all of those solutions, our stock and the 3 solutions that we've just made, and measure the absorbance. So now that we've done this, we'll go to the next step. Which of the following samples should be used as a background blank to calibrate this spectrophotometer? Choose the best answer. And remember, we talked about this. We need to make sure that we take out the color from that yellow solution. And the yellow solution was that iron 3 nitrate solution. So I'm going to enter iron 3 nitrate and say, okay, we're done now. Hey, we did it. Okay. So we're going to use a clean Pasteur pipette to transfer the following solutions into 3 of these lovely cuvettes. So they're labeled. Yes, they are cuvettes, but I see that this is the blank stock S 1, 2, and 3. Okay, so test your pipette. I'm going to take my blank and put it in this one. Get rid of that. Take my stock down. Take my solution 1. Put it in that one. Solution 2. And solution 3. This one. Use the wipes to clean off all of our stuff. Okay. And then we're going to place the cuvette containing the iron 3 nitrate solution into the spectrophotometer. We're going to select calibrate. And we're going to remove the cuvette and put it back in the rack. So now I'm going to put the stock in there. Put this 447 is the wavelength that we're looking at. Sorry, it's bugging me that I'm not writing anything down. For 7. So why? You know that? You're fine. You're in pain. Zero 0.381. Four four seven. I mean, it doesn't like me. Okay. It's having problems. I apologize. It's in the wrong place. Okay. So that was our stock. Now I want to do And there's all of our samples. I can take this guy out and put that in there. Ta-da. Data. Should be good there. Right. So my x-axis variable is going to be the concentration. My y is the absorbance. And I want it to be a line graph. And I want to create that. One. Oh, that's right. I do want it to be a scatter plot. And then apply a line of best fit. Show linear regression. And can I? Okay. Y equals 1270x. And that 1270 is my molar absorptivity. It's the slope of the line. Cool. Oh, I didn't save it. Oops. Jeez. Okay. All right. 5 mil. Transfer 5 mils of 0.5 or 0.004 molar each test tube. I'm just recording exactly what they asked me to do. And since I've done them doing that, I'm going to record exactly what they want me to do because I have to do that. Otherwise, they won't let me do anything else. And this is where, if I was in the physical laboratory, I could make mistakes. And I might not necessarily be able to notice that. So if I didn't have good skill in using the pipette, I might not notice that I didn't get the exact right volume. And therefore, I might not notice that I have a potential source of error. All of those errors are extremely cumulative. And so if my calibration curve isn't very good because I had errors in the calibration curve, then I'm going to have errors from everything that I determine off of that calibration curve. This is where this becomes a problem because, having done the lab in 110 where we didn't make any solutions, this can be really problematic because you don't have the experience working with those pipettes. And if you remember working with the pipettes, if you actually did work with them, like that one lab where we worked with them at the very beginning of 110, they're hard to work with. They really are, and they require a lot of skill to get right. So asking you to do this experiment in the lab as your first experiment is a really big ask. So here, it's much easier for you to see the value in this lab if you can't screw it up. You can get data you can actually work with in this environment where it's not screwed up. And so the data that you have will give you results that you can actually look at and work with, as opposed to now I have data that doesn't actually mean anything because it's very flawed. And I have to figure out, okay, where did the flaws come from? What would I do different next time? And what do I do with the data that I have because it doesn't mean anything? So you're not getting the what we call it like to call educational value out of the lab because it didn't work. Okay? So that's not really helpful when it doesn't do what it's supposed to do. In my opinion, we need to modify what we're doing and how we're asking you to do. Got to write it down. And of course, the reason that we add the distilled water to this is we want to make sure that all the volumes are the same. It makes our math a little bit easier. Calculate the initial iron concentrations. Okay. Now we already looked at this. Pull it up again. How to calculate the initial concentrations. So we need to find the total volume for everything that we put in there. So how much of everything we put in? They have some example data that we put in there, right? And then our initial concentration is going to be the concentration times the initial volume divided by the final one. Okay, we can do that. Same thing is going to be true for the SCN minus. So it's going to happen for both. We have to look at our own data rather than the data, the sample data that they've given us. I've already put this in my lab notebook, so I'm not going to worry about it for right now. I need to look at the data that I have right here. So I have 5 milliliters of that Fe NO3. Oh, 8. So I have that FeNO3 and the volume of that equals 5.00 milliliters. And the concentration of the FeNO3 that we use equals the 0.00400. And I know that because that's what it says right there. They're both 0.00400 molar. Okay. And then the volume final of this is going to be this right here. So the sum of those. 5.00 milliliters that we started with, plus the 5.00 of KSCN that we added. So it's going to be 10 milliliters. And that should be true for all of those. We look across, 5 plus 4 plus 1, 10. 5 plus 3 plus 2, 10. 5 plus 2 plus 3, 10. And then 5 plus 1 plus 4, 10. So all of them are 10 milliliters. The only thing that's going to be different is how much of each of these things do we have. Now, all of the FeNO3s are the same because it's 5 milliliters for each one of them. It's the KSCN that's going to differ each time. So that we will have to calculate for each one of these. This calculation, we don't have to do once. The FeNO3. So if I want the concentration of FeNO3, a final one, so subscript F is final, equals the initial molarity, so subscript I, E3, I, is the initial volume, over VF. So my initial concentration, 0.00400 times the 5 milliliters that I started with, divided by the 10 milliliters that I end with. And that's going to give me 0.004 times 5 divided by 10. 0.00200. Half of what I started with, which makes sense to me because I diluted it by half. So that's surprising. So the initial concentration of this one is 0.00200. 0.20, 0.200, 0.020, and 0.02. Okay. When we look at that SCN minus, things are a little bit different when we talk about that one. So we talk about the volume, the SCN initial. So the initial volume of the SCN minus that we put in was 5. The volume, final volume, is still 10. And the initial concentration of the the KSCN, because that's where it came from. KSCN. 0.00400 molar, because it's the same concentration that we started with. So that initial solution is again 0.0020 molar. Okay. This one is exactly the same. So 0.00400 molar. So this calculation looks exactly the same as that one, right? It looks exactly the same as what we did here. Things change when we start looking at different volumes of that KSCN. So if our next one, we only have 4 milliliters of KSCN, so our volume of the SCN initial 4.00 milliliters. The final volume is again 10 milliliters. And the concentration of that KSCN zero point zero zero four. And I am flipping between the SCN and the KSCN as if they're the same. And that's because the counter ion, the K plus, is not really involved in this. So I am doing that. And, again, because it's a spectator ion, I'm not concerned about it. If you were in my class when I talked about spectators are just standing around. They are not part of this. And that's why we write those anionic equations where they're not involved. It's very easy for us to ignore it because they don't do anything. So that's part of why I do this. Okay. So if I want to calculate the concentration of the SCN minus final, that's going to be equal to the initial concentration at 0.00400 molar times the initial volume that I used, that 4.00 milliliters, divided by the 10 milliliters. So I can calculate that. 0.004 times 4 divided by 10. And that's 0.00016. And so by comparison, if we look at the changes as we go across, since the next one is going to be 3, total volume is still 10. The only number that's going to change is this one on top. And so we're going to keep changing that. We're going to go 3, 2, and 1. So I'm going to do 0.004 times 3 divided by 10. 0.00120. 0.004 times 2 divided by 10 would give me 0.00800. And then this last one, 0.004 times 1 divided by 10. And that's that 0.0004. And everybody seems to be happy. Yes, I love it when they're happy. That's awesome. Yeah. So now we should be good with that. So I'm going to move this. This here. Let's calculate that. Yep, I've done both of those. And so we're good. Yay! Use clean pasture pipette to transfer the following solutions into separate 1 centimeter cuvettes. Solution 1 goes in 1. Solution 2. I wonder what happens if I try and put. Oh, good. Wondered if it would just automatically do it for me, if it would tell me I'd screwed it up. In real life, it will let you do that and you won't know that you did it. And then it's like, crap, did I screw that up? Because it's really hard to tell when you put it in here which one is which. So that becomes fun, and then you have to start over. Okay, so now we use the wipes to clean everybody up. And we're going to place the cuvette, placing the solution into the cuvette. Don't do this to me. No, 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 no. No, you're not going to do this. You are not going to do this. I do not want you to do this. So it was all hung up on me, which it does from time to time. So first when it does that, God, I'm kidding. And sometimes it will do this. And you go to reset the phase. And you come back in to try it again, and it's still all hung up on you. And you say, okay, fine. Now, I understand that I haven't finished. So I have a choice. I can either submit it as it is, or I can exit. And it's up to you which one you do. It is hung up. It is not going to do anything for me. So I'm going to say, you know what? Okay, fine, bye. It has timed out because Alex has timed out. Because it took us too long. So we come back into Alex. Go through roster because I gotta go all the way through this. And then I go back in here. I go back to my student view. And what it should do is take me right back. Yes, here. And I should be able to pick this up. Come in here, take this, put it in there, and put that. I don't understand why it does that, but occasionally it does. So if you see that the window says notice behind it, then you can get screwed. I hate that, but there's not much you can do about it. Okay, so now we've got these. We're going to clean them up. Which we'd already done, but okay. Now I can put this in here and I can measure that. And so I can go to my lab data, and over here, I can say 0.784. Can take this one out, this one in, measure that 0.587. Point 474. Zero 0.369. And 0.165. Now we need to calculate the thiocyanate complex ion concentration in molarity for each solution. Now, I said, sure, right. How am I supposed to do that? And I know it's got something to do with the calibration that we did and the chart that we created. But I see that I have this how to determine this concentration. So I'm going to open this and I'm going to go ahead and copy it. And put this over here. Because this is that next thing I'm gonna have to do. And what does it say? It says the slope of the calibration curve, that number that we wrote down. The molar absorptivity is that number, and the absorbance is this. Using the measured absorbance, the molar absorptivity, and path length of the cuvette, calculate the concentration of the iron thiocyanate complex at equilibrium. The path length for the cuvette is exactly 1 centimeter. So the concentration is going to be equal to the absorbance divided by the molar absorptivity times the path. So I'll take that number that I measured, that absorbance, divided by the slope times 1. And that's how I'm going to do this. So I'm going to write that down. So concentration is equal to absorbance divided by the molar absorptivity times the path. So that's what that said. That's out of the way. I'm going to close this. And so I'm going to look at all of this stuff that I have. So that molar absorptivity is that number that we wrote down previously. And that was 1270. So that's that number that we wrote right here, molar absorptivity. And then I know that these absorbances are what we need to be looking at. So I'm going to go ahead and write down all 5 of them so that I will have. And I won't have to keep coming back to this. And then I can calculate all of those values that I need. And then I can come back in here and write them down. So I'm not really great at doing the whole 2 things. It doesn't really like to do this. Yeah, maybe it'll be okay. Okay. So So that I wrote down those 5 values right here. So 784, 0.587, 474, 369, and 0.165. I know the molar absorptivity, that's right here, and that path length again is 1 centimeter. So I can just ignore that. So my concentration is equal to that 70 divided by that epsilon. So that 0.78 times the mole, because I'm wrong. So concentration is going to be equal to 70 divided by 0.78. Seems really weird to me, but let's see what happens. Three sig figs there, 3 sig figs there. So I end up with this number 161. But there are only 3 sig figs in the numbers that I'm looking at. So I would round this to 1620. We'll see what it says. And it's not complaining. So I'm okay with that. So again, coming out with this 2163 3 sig figs, I'm going to report that as 2160. Okay. $26.80. So it's going to be huge. Huge. Yeah, it doesn't like any of those. Okay, so let's take a look at this again. This one. And this one. Oh, I did it backwards. That's why. Doofus. I should have put the absorbance on top, not the molar absorptivity. That's why. Hello. Okay, brain is here somewhere. So 0. 0.784 times 70. That looks a lot better. I knew there was something funky about it, but 0.784 70. And if my math is right, that's 0.000061736 figs. I'm gonna go ahead and delete all of these. Six, one, seven. We'll see if it actually makes that any better. So next one is going to be 0.587 over 1270. Zero point 0.0462. We're at a 0. Let's try this next one. It is 0.474 divided 270. 0.000373. 0.369 divided by 1270. 0.00029. 0.165 divided by 1270. 0.00130. Okay, I feel a lot better about that. All right. So that got us our equilibrium concentrations. Now, I can come in here and I can say, all right, how to calculate the equilibrium concentrations of the iron. And he knew this was coming because I said it was coming. We were going to do ice tables. And this is where the ice tables come in. Again, I'm going to put this in here because I knew I was going to need this. And what I'm going to have to set up is an ice table. So remember that this is technically a rice table. And that reaction that I'm looking at is Fe3 plus the SCN minus into that FeSCN2 plus, because that's how I like to. Initial concentrations are that 0.0004. Actually, that's their example, but I'm looking at the numbers that we had 0.00400, 0.00400. And I know that because I remember that because it's right here. So I know that was the same number for both of them. That's why I'm writing it down. Okay. So my initial FeSCN concentration, I'm pretty sure that we wrote that down. Did not, but that's okay. We can think about that in just a second. Now, I know that every time I make an FeSCN, I need one of these to make it, and these to make it, and I will get one of these. And I know at equilibrium, this will be this minus the x is the x, and then this is going to be plus the x. And so if I think about it, initially we have none of this. And the concentration of this one, we actually measured. So we measured that, found that to be, for this first solution, that x is equal to 0.000617. That's the numerical value that we found. So since I know what that value is, I know that that's equal to x. So x is equal to this, so I should be able to calculate this and this. So if I come into my calculator, I say 0.004 minus 0.000617, and that gives me 0.003383. I get really tired of doing all of this manually, so I get lazy. And so I come in and set up an Excel spreadsheet for myself to do this. And the way I always do this is to set it up so that I have the initial concentrations and then the equilibrium concentration here. I usually leave the C out just because I know what it is, but it makes you feel better that you can do it. So this is my Fe3 plus, this is my SCN minus, and this is my FeSC2 plus, and I can do the whole superscript subscript if I want to. It's totally possible to do that. I have these set up as short keys because I use them all the time, but you can get to them by going to font. There's superscript and subscript right here. So if you're neurotic like me, you can do that. If you really want to add them to your ribbon, you can do that too, because I have done that. And so what you can do is you can come in and customize the ribbon, and then you can search for them in here. They'll be down here under, subscript, superscript, and then you can add them to whatever you want to. I have added, as you can see, there's a little section that I call chemistry. built a custom section where I put things that are useful to me in that stuff. So just makes my life a lot easier to have that. So these are the concentrations there. This is my concentration that I solved for here, 0.0617. And actually, I can set this to be so I can put that molar absorptivity there. And this is the absorption. So then this is equal to the absorption divided by absorptivity. Since I want this to always be that value, then I can make it like that. And then I want this to be equal to this divided by that. And that's to be equal to minus that to be equal to that. And so that sets it up. And I can do, I can copy and paste this anywhere I want. And so every time I set this up, I have a new absorption that I put in for the next value. And it calculates new concentration. So as long as I know exactly what I'm talking about in terms of what those are, and I know that the concentrations are the same, and I know that they are for the Fe3 plus in each situation, then that's fine. I know that they're not necessarily the same for each of these in terms of, and actually they aren't for the Fe3 plus, and I need to fix that. So I will need to fix that because my initial concentration of the Fe3 plus is 0.2. That's right, diluted it. And in this first situation, that was true for the SCN minus, but it was not true in the other ones for the SCN minus. And so I can set that up to be that calculation, and I often do. But that way I can have it calculate that automatically for me. For me, this is just a lot easier because I know how this works. I know how the rice table works. And so when you get really comfortable with rice tables, you can get to a place where this is helpful to you. Initially, this will look like it will make no sense. And I understand that. You used to give people spreadsheets to help them with this lab, but I found that it's not helpful if you don't know what they are. You have to have the experience of building them to make this work. And so giving it to you was not helpful. Making you build it can be helpful, but only if you know what you're doing. Now I'm gonna have to pause here and stop this recording. I'm actually gonna have to come back because I have to go teach for class. So I'm gonna have to come back after class. So I'm gonna stop here and then I'll tack on another recording and we'll finish this out. So because we need to calculate the equilibrium constant once I'm done with all of these calculations. So I'll talk to you in a little bit. Bye, guys.